Hello everyone, and welcome to this video on factoring expressions containing rational exponents. And when you see the word rational, you should be thinking of fractions, right? So exponents that are fractions like 2/3, -2/5, 1/8 or something like that. So in this video I'm going to go over a brief recap of what it means to factor out a common factor from an expression. And it's basically just reversing the distributive property when you factor something out of an expression with multiple terms. And then we'll look at some examples where the expressions in question have some parts of them that are raised to a rational exponent, a fraction exponent. Okay. All right, so hopefully you recall what the distributive property is, and I'll just kind of write that here. Right, the distributive property for real numbers is if I were taking some number, some expression representing a number called a, and multiplying it by, notice there's no plus or minus in between here, no positive sign, no negative sign, so there's touching that's implied, multiplication. And then in parentheses you have a sum or a difference. So I'm just going to put a sum in here because a difference, with subtraction is the same as a sum, right? Subtraction is just adding the opposite. So say I have in this set of parentheses, b plus c. All right. Well, this is equivalent to, this is the distributive property where you take the number out front and multiply it by each term in this sum. Again, this is only good for sums and differences, right? This is a sum in here. You see the plus sign, or differences. And you can do what's called distributing. A times b for the first term of an equivalent expression, then plus or minus, and then a times c. Okay. All right. So what we did when we factored out a common factor, and I did this in a video a while back, factoring out the greatest common factor of an expression, was just go the other way. You started with an expression like this and you looked at the terms. Okay, and remember, terms are products, so this is a term here with this a times b, and then they're separated by a plus sign. All right, so this is a term plus, and then this is another term. Okay, another product. All right, and what you looked at was, you looked at each term and looked for what was a common factor, what was a common part of each product. And these terms here would have a common factor of that capital A, right? That capital A is part of the product in both terms, right? A times B, A times C. And then so you go this way by, you just rewrite the expression by doing what's called, factoring out that common factor. The common factor comes out and becomes its own factor. And then in parentheses you have what are left over in the terms when you remove that factor of A. Okay. An example of this that you might be familiar with, I'm going to do an example here where we have whole number powers. So if I had, for instance, say x to the third power plus 2 times x to the second power, and there are this is a term, x cubed times 1, if you want to think of it that way. This is its own product, plus, and then this is another term, a product, 2 times x squared. So when you were looking for common factors, now if you wanted to, you could write this out as x times x times x, right? What it meant to be x to the third, plus, and then 2 times x, right? What it meant to be x squared. And then you look at these two products, these two terms, and say, what's in common? Well, they have an x, right? But they also have another x, right? So it looks like the common factor here that I'm going to be pulling out is, x times x, or other words, x squared, right? That means x times x. Now, one way also to look at this x squared here, this is the common base that the two terms have in their products, right? They both have, both of these terms have a part of the product. A part of the term has a base of x to some exponent. So there's a base of x to the third 3 exponent, and this term has a base of x to the 2 exponent, right, to the second power. This common factor that I'm pulling out, you could also think of as the common base x raised to the lowest power that you see. Raised to the lowest, the smallest power of that common base, right? So this is the way I'm going to think about this, this common factor stuff for this particular video. So I look at these two terms, right? They have the two terms have a common base of x, right? They both have x to some power, and the lowest number of those powers of 3 and 2 is 2, right? So I'm going to factor out an x squared, right? So we factor out x squared, and this will leave me with this equivalent expression here. So this expression here, x cubed plus 2x squared, will be equivalent to this x squared comes outside as its own factor times, and then there were two terms here. There are going to be two terms in parentheses, so that imagine I were redistributing the x squared. What would need to be in here and here? What two terms would need to be there so that when I redistribute x squared, I'd get x cubed plus 2x squared back. And one other thing I need to point out, one other thing we need to remember is a certain property of exponents. So one more recall down here, that when you multiply x to the nth power by x to the nth power, right, when you multiply two things with the same base, you keep that base, and the exponent, the new exponent, is the sum of the previous two, right? The new power be m plus n. So if you keep that in mind, you got to think, here I have x squared. What would be the power of x in this first term, so that when I multiply them I get x cubed? So 2 plus what would be 3? Well, 2 plus 1 would be 3. So I'd have x to the first power. You can write the 1 there if you want. But when I multiply these, x squared times x to the first, I'd get the first term up here, x to the third. All right, then plus, right, in parentheses. And then the next term has 2 times x squared. Well, I pulled the x squared out, so the x squared is gone, leaving me with just the 2. Right. So here's how we would factor, x cubed plus 2x squared, right? These terms where we have whole number powers. So it ends up being x squared times the quantity x plus 2, or x to the first plus 2. Great, so hopefully that rings a little bit of a bell. If you've seen it in your texts or in previous videos of mine or other people's videos, I'm hoping that you've seen that at least before. And remember this property for exponents, and also the distributive property, and what we're doing is reversing it. We're going this from right to left here. So I'm going to do basically the same thing now, but in the following examples, parts of the terms, some of the bases in the terms, will have a fraction for an exponent. Alright, so here I'm asked to do the following. Let me get rid of this. Okay, so I'm asked to simplify And look, I have two terms, right? Two products. This is 8 times x to the 3 halves power. So that's one product, one term, separated by a plus sign. We're adding plus, and then this whole thing, right? If an expression is in parentheses, you can think of it as, one particular letter, one variable. Like 4x plus 3, you could think of that as y or something, right? Some other letter. But this is all considered one factor. So I have 3 times x to the half power, 1/2, times, and then this 4x plus 3 again is all considered one factor because it's in parentheses. So that whole thing, right, all of this is considered one term, right? So I've got a term here, and plus, and then a term here. Alright, so looking at these terms, now I wrote down what we're going to do. We're going to factor out the common factor of x to the half. And as I mentioned on the previous page, look at this, x to the half. This is the common base of the terms, right? Because look, this has 8 to the first and x to the 3 halves. This has a base of x to the 3 halves power. This has 3 to the first, x to the half, and then 4x plus 3 to the first, if you want to throw a 1 out there. But so it has these bases. The base they have in common is the x, right? They both have x to some power. So this x to the half is the common, when I'm making the common factor that I'm going to pull out, is the common base raised to the smallest exponent or to the lowest exponent. So look at those exponents on the x's. There's x to the 3 halves in this term and x to the 1/2 in this term. Which number is smaller, positive 3 halves or positive 1/2? Well, thinking about a number line, 1.5 is bigger than 1/2, right? So 1/2, x to the half, this is the smallest power. I'm going to factor that out, factor out x to the half. All right, so let's see what happens when we do this. All right, so this expression I started with, all right, will be equal to, I'm factoring out the common factor. I'm factoring out this x to the 1/2 power, right? So x to the 1/2 power comes outside, times, right? Times, and no plus or minus here. And then in parentheses, this expression had two terms. So this expression is going to have two terms, the thing inside the parentheses. And it's going to be, what would I need to have in here so that if I were to redistribute x to the half, I'd get my original expression back, right? And don't forget this property again, right? Keep it up on top here. Remember this property. When we multiply two things at the same base, you add the powers. Okay, so in the first term, in the parentheses, right? I have the 8 still, right? I didn't remove any part of 8, so there's still 8 here. Times, and then I didn't remove x to the 3 halves, I removed x to the 1/2, right? So there's still going to be some x left, but how much, right? What's the power on this x? Well, think about it. If I were to take x to the half and multiply it by x to some power, what would this power need to be so that 1/2 plus that power is 3 halves? Well, 1/2 plus 2 halves would be 3 halves. So 1/2 plus 2 halves would give me what I want. Well, what is 2 halves though? What is 2 divided by 2? That's 1, right? I don't need to write 1. If you just write x, it's x to the first. So the first term in here is going to be 8x when I remove x to the half. Hope that makes sense again, keeping in mind this property of exponents. Plus, right, and then the next term, what's left over? Well, I've removed this entire x to the half. So there's no more x to some power like there was in the first term. I removed the entirety of x to the half. So the only factors left in the second term are the 3, and then times, and then the other factor left is the 4x plus the quantity 4x plus 3. All right, notice it's still in parentheses, it's all one quantity. And there we go. I have now factored out this x to the half from both of these terms. We have this equivalence here. All right, now we are asked to, simplify. So I noticed that there's going to be some in this big set of parentheses here, inside here with the 8x plus 3 times 4x plus 3 here. There's going to be some like terms that I can combine. I can't do it yet. I can't add 8x and 4x. I need to get rid of these parentheses. It's like a wall. I need to take down that wall by using the distributive property here, multiplying the 3 by the 4x plus 3. Okay, so we have outside still the x to the half that I factored out earlier, and then I'm working just inside this set of big parentheses. We have the 8x from earlier plus, and then when you distribute, that gets rid of the parentheses, right? Remember the property earlier. When you distribute, there are no more, the parentheses are removed. Okay. So this 3 times the quantity 4x plus 3, 3 times 4x is positive 12x. And then 3 times 3, positive 9. And, now, look at this. This expression inside the big parentheses goes from being 2 products, 2 terms, to 3 terms, right? There's 8x, 12x, and 9, all separated by plus signs. So it went from 2 products, 2 terms, to 3 terms. But we're going to combine, like terms. There's 8x plus a 12x. Both of these have x to the first power attached. So I can combine them, make what's 8 apples plus 12 apples? It's 20 apples. So this is 20x when it's all said and done. So again, this is equal to x to the half that got pulled out earlier times, and then 8x plus 12x, 20x, and then the plus 9 doesn't go with anything. And again, this is all still inside that big set of parentheses. All right, and then is this completely simplified? I mentioned a couple videos ago on simplifying radical expressions or expressions with rational exponents. When they mean by simplify in most intermediate algebra or beginning algebra texts, will mean have all positive exponents, which this exponent is positive, it's x to the positive 1/2. This is x to the first, so again a positive exponent. So all positive exponents. Then no powers to powers, right? And I know there was another rule in the video a couple of videos ago where it said you don't want to see the same base more than once. Well, that was specific to when you had just a product, just a single term. Notice there are multiple terms in this, so you're gonna see the same base more than once. It's just going to happen. You can't really avoid that. So I'm not going to throw that in here. We're not going to worry about seeing the same base of x twice because there are multiple terms. Okay, and so there we go. Positive exponents all around. No powers written to powers. So I'll put this in a box here. So our expression in the beginning should be equal to this expression here. And let's test it out. All right, I'm going to test this out. Now before I do though, I'm going to point something out about the value of x. What's allowed to be plugged in for x. Remember our fraction exponents. Look at the denominators on these. They're both 2. So that means I'm going to be taking an even root, the square root of x, and then cubed, and then this is the square root of x. So remember, when we're dealing with real numbers, if I want a real number output, the value of x needs to be non-negative, right? And again, so this is like the domain of the problem, right? What am I allowed to plug in for x? I'm only allowed to plug in non-negative values, 0 or greater. Because if you plug in negative values for x, this will be a non-real number. This would also be a non-real number. Okay, but I want, again, in most intermediate beginning algebra texts, we're dealing with just real number outputs. Only I want a real number output. All right, so let's test it out. Are these in fact equivalent? Is the expression I started with actually equal to the expression I got at the end? Well, if they are, then they should be equal for any value of x from the domain, anything that's allowed. All right, so I'm going to pull up a calculator here and we'll mess with this. So up here, I'm going to plug in for x. I'll plug in, again, anything that's non-negative. How about 5? All right, I'm going to plug in 5 for x. So this first term, I had to have 8 times, and then 5 raised to the 3/2 power, okay, plus, and then 3 times, and then x, again, I'm letting x be 5, so 5 raised to the 1/2 power, times, and then in parentheses, 4 times 5, right, I'm letting x be 5, plus 3. Close parentheses. All right, let's see what this value is. Probably some crazy value. All right, it's 243.7314095. Probably some irrational number where the decimal goes on, forever without ending, without repeating. Okay, so let's keep this number up here. And let's look at the expression I got in the box at the end. Is this truly equal to this? Well, up here I replaced x with 5, and got a value of 243.731 something. Let's see what happens down here when I replace x with 5 down here. Alright, so the first factor is 5 to the 1/2 power, 5 raised to the 1/2 power, times, and then in parentheses, 20 times 5 plus 9, and then close the parentheses. And I'm hoping, if what I said is true, if these are truly equal, then I should get the same number again here when x is 5. And look at this. It is 243.7314095, and so on. All right, and try that out with other ones. So again, plug in only non-negative numbers for x, because I want a real number output. Plug in 7 for x up here and 7 for x down here, and you'll see you get the same number. It won't be 243 again. It'll be something else, but they should be the same value all the time, as long as you plug in a value that's in the domain, plug in a value that's non-negative. So try that out on your own with some other values. All right, so I've got just one more example here where I'm doing the same instructions. I'm asked to simplify some expression with multiple terms, right, separated by plus signs. So products separated by plus signs. Some expression with multiple terms. I'm going to be factoring something out. I'm going to factor out that common base raised to the lowest exponent, all right, and see what we get. All right. So same type of example here. I have simplify 9 times x to the 1/3 power. That's one term, right? One product, plus, and then here comes another term, x to the negative 2/3 power, right? Another x to a fraction, times, and then again, this is in parentheses, so it's all considered, that's all considered one factor of this product. So this again has just two terms. This is a term, the 9 times x to the 1/3. And this is a term as well, right? This times this times this, two factors here. Okay. So looking at these terms, right, now I already said I'm going to be factoring out the common factor of x to the negative 2/3. But again, that's this thing here. That's this common base raised to the lowest power. Let's look at these two terms. Look at these two terms. There's a base of 9 here. There's no factor of 9 over in this product. There's a base of x. In this term, this product, there's also a base of x. So they do have a common factor. All right, they both have x to some power in it. And then this one has 3x plus 1 to the first, and this factor, doesn't have any 3x plus 1s in parentheses. So the only thing they have in common, the only base that they have in common is x. So I have x to the 1/3 in this term, x to the negative 2/3 in this term, and which one of those numbers is the lowest? So this is a positive power, this is a negative power, right? Negative numbers are always lower than positive numbers. So I'm going to factor out, like I said here, x to the negative 2/3, the common base to the lowest power. All right, so let's do that. and see what we get. So this expression here, take down here, is equal to, pull out the common factor, right? Basically, I'm just reversing the distributive property. And again, we're going this way in the distributive property. Right, so I'll pull out this x to the negative 2/3 power, right? That'll become its own factor. So that comes out times, and then big parentheses, and then there were two terms here. I've pulled out this x to the negative 2/3, so in the parentheses there should again be two terms, and basically what's left over when I remove x to the negative 2/3, or think of what would need to be in here, what two terms would need to be in here, so that when I redistribute the x to the negative 2/3, I'd get my original expression back. And don't forget this property here will help. So the first term, I didn't pull out anything to do with 9, so 9 is still there. And I didn't pull out x to the 1/3, right? I pulled out x to the negative 2/3. So there's still some power of x, still some of that left. And again, let's think. What does the power on this need to be? X to what power? Well, if I were to multiply these, x to the negative 2/3 times x to some power, I want that to be x to the positive 1/3. So, negative 2/3 plus what would give me positive 1/3? Well, negative 2/3 plus 3/3 would give me positive 1/3. So the power on x in here needs to be 3/3, or 3 divided by 3, which is just 1 again. So all I'm left with here in this first term, after factoring out x to the negative 2/3, is 9 times x to the first, or just 9x. Wonderful. Plus, and then the next term, the next product, I removed this whole thing, this x to the negative 2/3. That's out. That's coming out. So that's gone, and I'm left with this quantity 3x plus 1. And I'll close the parentheses. And can you see how if I were to redistribute, if I were to take this x to the negative 2/3 and multiply it by the 9x, I'd get 9x to the 1/3 back. And then multiply it by this, I'd get the x to the negative 2/3 times the 3x plus 1 back as well. All right. Now, this is great. It is factored, like they asked, but we're also asked to simplify. So look inside this big set of parentheses. There are some like terms. 9x plus, now really the parentheses aren't necessary here anymore. In the previous example there was a factor of 3 that I could distribute. Here there's a factor of 1 technically. When you remove a whole factor, you technically leave over a factor of 1. So if you want to, you could say, oh, I'm distributing the 1, but anything times 1 is itself. So what this is equivalent to would be x to the negative 2/3 power times, and then you have the 9x plus, and then again 1 times anything. If I'm distributing the 1, that'll get rid of the parentheses. 1 times anything is itself. All I'm left with there is 3x plus 1, and I can remove the parentheses now. Right? Not really necessary. And look inside again the big set of parentheses. There are some like terms. There's 9x and 3x. Those go together to make 12x. So this is x to the negative 2/3 power times, and then 9x plus 3x makes 12x, and then you got the plus 1 still in there, and close the parentheses. Alright, and this is great. I like this, but again though, in most intermediate or beginning algebra texts, when you're asked to simplify an expression with exponents, they're going to want you to rewrite things so that there's no negative exponents. So off to the side here, I'll put hopefully something you remember from a previous video of mine, or if you've seen it in your book or some other video. Remember, anything to a negative power, right, any non-zero number to a negative power, is just the reciprocal of that same non-zero number to the opposite of that, to the positive power. And again, I'll say that a can't be 0 here. Right? So I can use this property here. Right, when I see x to the negative 2/3 power, this is just, I'll write this off to the side. When I'm seeing this x to so negative x to the negative 2/3, this is, just 1 divided by x to the positive 2/3, right? It's just the reciprocal of x to the positive 2/3. So all that does is it puts x to the positive 2/3 in the denominator. You see that here, right? Numerator 1, denominator x to the 2/3. So in writing this without negative exponents, I have this factor of 12x plus 1 in the numerator, and since it is the only factor left, right, the x to the 2/3 goes to the denominator, and since that's the only factor left, the 12x plus 1, I don't need parentheses around it. And again, x to the negative 2/3 is 1 over x to the positive 2/3, so that puts x to the positive 2/3 in the denominator. All right, so most, again, intermediate or beginning algebra textbooks would expect, this answer. Rewriting things so that, all the exponents are positive. Okay, great. So I'll pop that up here. So the expression I started with, all right, is equal, or should be equal to, this expression here, where 12x plus 1 in the numerator and x to the 2/3, positive 2/3 in the denominator. Let's test it out. All right. Now last time, right, the previous example, the denominators on my exponents were even, so I didn't want any negative bases. Right? I didn't want to plug in non-negative. I didn't want to plug in negative numbers because the result wouldn't be real. Here though, both of the denominators in my powers are odd. And remember from previous videos, you can take an odd root of any number. So I'll mention that here. So the domain for this expression, I'll just say x can be anything. You can plug in any real number you want for x, except 0. Because look at this the way it looks at the end. Remember I even mentioned here, right, with the little negative power thing. When you have something to a negative power, well, you can't raise 0 to a negative power because you'll end up dividing by 0. Right. So back to this, the value of x can be any number except 0. Right? I don't want to be dividing by 0 at the end. Have 0 in the denominator. That's undefined. Right? Can be any real number except 0. Or just simply put, x cannot be 0 like that. Right? All right, so plug in anything else you want. I'm going to test this again with my calculator. I'm just going to let, I don't know, let's have x be 11. Right, that's not 0. And let's see what we get. All right, so here's the calculator I got, and go back to our original expression. I'm going to plug in 11 for x. 9 times 11 to the 1/3 power, so 11 raised to the fraction 1/3, plus, right, then the next term, the next product, again I'm having x be 11. 11 raised to the negative 2/3 power, times, right, times is touching, and then in parentheses, 3 times 11 plus 1. Okay. That's the first expression I started with, where all the x's are replaced by 11, and the value is a real number. As I mentioned, it will be real, and it's the number 26.8899411, so on, so on. It's most likely irrational, where the decimal goes on forever without ending, without having repeating pattern. All right, so that's what I got with the first expression. Now, if these truly are equal, like I'm saying, they should be equal for every value in the domain, right? No matter what I plug in for x. So I'll plug in 11 down here. Now I'm going to put, parentheses around this because this all these terms are in the numerator. So in parentheses, I got 12 times, x, but I'm saying x is 11, plus 1. close parentheses, that's the numerator. Divided by, and then I'll do the same with the denominator. I'll put it in parentheses. I know there's only one term, but I'll just put it in parentheses anyway. And then x to the 2/3, or 11 to the 2/3 power. And if what I've said is correct, if everything I've done is correct, these should be the same value. And look at that, they are, right? 26.88994111, so on and so on. And try it out with other numbers, right? Just not 0. Right? Try this out with other numbers. Plug in, 7 for x. Plug in -8 for x. You can do negatives this time because you're only taking odd roots. Plug in, -8 for x up here and -8 for x down here, and you're going to see that they will have the same value. Not always 26.88 something, but they will have the same value as long as whatever you plug in is not 0. Great. So it looks like I'm good. Looks like these are equal. Wonderful. And I've written it without, without negative powers. Great. All right. I like to say at the end of these videos, try your best to learn the material on your own before you go looking for help. Because I find people that put in the time and effort to learn things on their own tend to remember it better and remember it for longer. So, of course, read the material, read through the author's examples, perhaps even try to work out solutions to the author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, do plenty of exercises, practice problems, look up solutions to those whenever they're made available to you. And just so you can check your work, keep track of your progress. And don't just give up on a problem after one attempt. Very often in mathematics there are several approaches that'll work for a problem. So if after several approaches, several attempts at a problem, it's still not making sense, you're still not getting it, perhaps you should go back and read the material again. Maybe even a third time. More slowly, more deliberately. Take notes. Because if you've been working on some problems, you probably have a better idea as to what the author wants from you, what the author's asking of you. So that'll give you also a better idea as to what to look for when you read through the material again. Perhaps you'll see some things that you didn't see the first time that'll make working on the problems that much easier. But if after that, if after several read-throughs of the material, several attempts at the problems, you're still not getting it, still not clicking for you, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online on the subject. There's tons of those too. Videos like this one, or plenty of other ones out there that are better than mine. I assure you they're out there and they're easy to find. But all I'm saying is just stay persistent. Don't give up. Keep practicing. And I think above all, I think the hardest thing too is to try to stay positive about the subject. Try to stay confident. Even if you are struggling, you have to fail to learn. All right, struggling and failing are part of learning. That's where you do your best learning, is when you realize you've done something wrong and can fix it. So try to stay positive through all those failures, all the struggles, because if you stay persistent, keep practicing, and stay positive and confident, and don't give up, you'll eventually get through it. You'll eventually get the material. I know you will. All right, so just keep at it, and thank you very much for watching.